You ever notice how some things in life just seem to follow a pattern? You know, like people's heights, or test scores, or even how long a product lasts? Well, it turns out there's a hidden order to all that randomness, and today, we are going to crack the code.
So this pattern is officially called the normal distribution, but you probably know it by its more famous name, the bell curve. It's this perfect, symmetrical shape that just pops up everywhere. And why? Because most things are the result of a ton of different random factors all working together. It just shows how most of the data clumps right around the average, and the further you get from that middle point, the rarer things get. It's the secret pattern behind, well, almost everything.
Okay, so if the bell curve is the map, then the empirical rule, well, that's our secret decoder ring. It's a super simple but incredibly powerful shortcut that lets us understand how all that data is spread out without needing to bust out any complicated formulas. You'll also hear it called the 68, 95, 99.7 rule, and those numbers are everything.
So here's the game plan for this explainer. First, we'll unpack the secret numbers behind the bell curve. Then, we'll use a bright idea, literally we're going to talk about light bulbs, to see how it works. After that, we'll do some calculations, solve a few tricky statistical puzzles, and at the end, we'll put it all together in one big picture.
All right, first up, let's break down those three magic numbers that give the empirical rule its name.
The first number you got to know is 68. This tells us that for pretty much any normal distribution, about 68% of your data, the vast majority of it, is going to fall within one standard step away from the average. And that step is what we call a standard deviation. So think of this 68% as all the normal, everyday, expected stuff.
Next up, 95. Now if we take two of those steps out from the center in either direction, we capture a whopping 95% of all the data. This covers almost everything, the totally normal results, and even the slightly unusual ones. And finally, 99.7. If you go 3 standard deviations out, you've basically got it all. 99.7% of every single data point will be inside this range. Anything that falls outside of this, man, that is a true outlier, a really, really rare event. So just lock these numbers in your head, 68, 95, 99.7. That's the code.
Theory is one thing, but let's make this real. We're going to use a super simple, practical example to see this rule in action.
Let's pretend we're looking at the lifespan of a certain brand of light bulb. On average, a bulb lasts for 50 weeks. That's our mean, and it's dead center on our curve. The standard deviation, our step, is 5 weeks. So 1 step up from the mean is 55 weeks. 2 steps is 60, and 3 gets us to 65. And if we go down, it's 45, 40, and 35. These are the key values we're going to work with.
Okay, we've got our map and our key values. Let's use the empirical rule to solve our first couple of puzzles.
So here's our first question. We want to figure out what percentage of all these light bulbs will last somewhere between the average of 50 weeks and the 60-week mark.
Okay, let's think this through. 60 weeks is exactly 2 standard deviations above our mean of 50. Now we know the rule. The total range within 2 standard deviations is 95%. But we only want the right side of that, from the middle to the 60-week mark. And since the bell curve is perfectly symmetrical, we just chop that 95% in half. So 95 divided by 2 gives us our answer, 47.5%. See? Simple as that.
All right, let's try one that's a little more fun. What percentage of bulbs last between 40 and 55 weeks? Now this time, our range crosses right over the mean.
The trick here is just to split the problem in two, right at the mean of 50 weeks. So first, let's look at the left side, from 40 to 50. Well, 40 is 2 standard deviations below the mean, so that's going to be half of our 95% block, which is 47.5%. Now for the right side, from 50 to 55, 55 is 1 standard deviation above the mean, so that's half of the 68% block, which is 34%. All we have to do now is add those two pieces together. 47.5 plus 34 gives us our answer, 81.5%.
All right, you've totally got the basics. Now let's level up and see how this rule helps us solve some more advanced statistical puzzles.
Okay, for this next one, you got to pay really close attention to the wording. What percentage of bulbs last less than 35 weeks or longer than 60 weeks? That little word "or" is the absolute key here. It tells us we're looking for the total of 2 completely separate areas, the far-out tails of our curve. Let's break it down. First, the area less than 35 weeks. That's 3 standard deviations below the mean. We know 99.7% of data is within 3 deviations, right? That leaves 0.3% for both tails combined. So that tiny left tail is just half of that, or 0.15%. Now for the area longer than 60 weeks. That's 2 standard deviations above the mean. We know 95% is within 2 deviations, which leaves 5% outside. So that right tail is half of that, or 2.5%. And since the question used or, we just add them up. 0.15% plus 2.5% gives us a total of 2.65%.
And this brings up a classic logic trap you have to watch out for. Look at the difference here. If a question asks for a bulb lasting less than 45 weeks and more than 55 weeks, the answer would just be 0. Why? Because a single light bulb can't have 2 lifespans. It's impossible for it to be in both those places at once. Or, on the other hand, just means you add the separate areas together. It's a really crucial difference.
Okay, time to flip the script. Instead of starting with a lifespan to find a percentage, let's start with a percentage, a percentile, and work backwards to find the lifespan. So what lifespan marks the 84th percentile? So don't let the word percentile throw you. The 84th percentile just means the point where 84% of all the data falls at or below it. We already know that the mean, right in the middle, is the 50th percentile. So to get from 50% to 84%, we need another 34%. And what does our rule tell us? Well, 34% is exactly the slice between the mean and 1 standard deviation above it. So we take our mean of 50 weeks, add 1 standard deviation of 5 weeks, and what do we get? Exactly 55 weeks.
We've covered a ton of ground, solving these problems piece by piece. But now, let's zoom out and put it all together. Let's see the entire empirical rule in one single, powerful picture.
This is it. This is the complete blueprint. It shows you how those big numbers, 68, 95, and 99.7, are really just built from these smaller, perfectly symmetrical slices. You've got the core right around the mean, made of 2 34% chunks. Then you've got the next layers out, which are 13.5% each, then the little 2.35% slivers, and finally, those teeny tiny 0.15% tails. Every single problem we've solved so far was just about adding up these specific pieces.
And here you go. This is your ultimate cheat sheet. This table doesn't just show you the percentage in each slice, but it also gives you the cumulative total as you move from left to right across the curve. This makes finding percentiles an absolute breeze. You can see right here how you hit the 16th percentile at -1 standard deviation, the 50th right at the mean, and the 84th at +1, which is exactly the problem we just solved. This one table is pretty much the key to any empirical rule problem you'll ever face.
So, there you have it. The empirical rule gives us this amazing framework for making sense of any data that follows that classic bell curve. From light bulbs to exam scores, this pattern is everywhere, and it's incredibly consistent and predictable. So that leaves just one last question for you. Now that you've cracked the code, where else in your world do you think this hidden pattern is shaping the results?